In this video, we discuss an important property of continuous functions, namely the intermediate value theorem. The theorem claims the following. Let f be a continuous function defined on the closed interval ab, such that fa is positive, fb is negative. Then we will be able to find some intermediate point c such that fc is equal to 0. Seen from a geometric perspective, this theorem seems to be fairly trivial. After all, if the function value at a is above the x-axis, and the function value at b is below the axis, then when we draw a continuous curve connecting a-fa and b-fb, naturally, it should intersect the x-axis at some point, namely c, and clearly fc is equal to 0. However, as one can imagine, the validity of this theorem is essentially based on the completeness of real numbers. Hence, any rigorous justification of this theorem should use one of the characterizations for real numbers. Here, we will use the nested closed intervals, and we will apply the theorem of Cauchy-Cantor. Now let us discuss how to construct the nested closed intervals. We will do it in a recursive way. Assume that a and b are given, so we got a closed interval ab, such that fa is positive, fb is negative. Let us call p the midpoint of a and b, and let us consider the function value at p. If fp is not equal to 0, then there are only two possibilities. Either it is positive, otherwise fp is negative. If fp is positive, we will keep the point b fixed, and we will replace point a by point p. In other words, we will take the right half of the original interval. If fp is negative, we will keep point a fixed, and we will replace point b by point p. In other words, we will take the left half of the original interval. You see that in both cases, the updated interval will always have two properties. First, the function value at its left endpoint is positive, and the function value at its right endpoint is negative. Moreover, the length of the updated interval is halved with respect to that of the original interval. To further illustrate this idea, let us look at this animation, which shows the first few intervals in our construction. As you can see, we first initialize the interval a now b now to be the original interval ab. From there, we look at the function value of its midpoint, which turns out to be positive. As a result, we take the right half of the original interval. And we will keep going, check the function value at the midpoint of the new interval, which turns out to be negative. Thus, in our next update, we will take the left half of the interval. We will keep going in this way. Check the midpoint's function value, determine whether we should take the left half or the right half, and then proceed to the next step. Each time, the new interval in this sequence is contained in all the previous intervals. Moreover, the length of the interval after the nth construction is equal to b minus a divided by 2 to the power of n. Alright, now you see that if we keep going in this way, there will only be two possibilities. Either the algorithm terminates in finitely many steps, meaning that after finitely many steps, the midpoint of the updated interval will have function value 0. If that is the case, we have actually found the desired point c, which is precisely this midpoint. And that is great. Otherwise, the algorithm will not terminate in finitely many steps, meaning that no matter after how many steps of construction, if we look at the last interval, the function value of its midpoint will not vanish, which means that we can continue for the next step of construction. But if that is the case, we have actually achieved the desired nested closed intervals. Let us recall the famous Cauchy-Cantor theorem states that the intersection of nested closed intervals in R is non-empty. Actually, in our case, since the length of the interval is halved each time, the intersection of the nested closed interval will be a single point, namely c. And we claim the function value at c is precisely 0. We can prove this by contradiction. If fc is not equal to 0, then without loss of generality, we can assume that fc is positive. Since f is a continuous function, we know that there will be a small open neighborhood inside which the function value remains positive. However, recall that the length of our interval a and bn is equal to b minus a over 2 to the power of n. In other words, as n becomes greater and greater, the length of the interval a and bn becomes shorter and shorter. Clearly, when n is large enough, the interval a and bn will completely fall into the open neighborhood that we have chosen for C previously. Now, on one hand, recall that along our construction, we have always ensured the function value at Bn is negative for any n. On the other hand, recall that we have chosen the open neighborhood for C in a way that all the points in this open neighborhood has positive function value. Thus, Bn should not be an exception, meaning that fBn should also be positive. Now it turns out that the function value at Bn should be positive and negative at the same time, indicating a contradiction. Thus, Fc cannot be positive. Using similar argument, we can show that Fc is not negative neither, leaving the only possibility that Fc should vanish. Now we have proved the intermediate value theorem. As we have mentioned before, this theorem is based on the completeness of real numbers. Thus, although the idea of bisection is more or less essential, apart from nicely closed intervals, there are surely other alternative approaches. For example, the Bolzano-Weierstrass theorem, the Cauchy sequence, and so on. We leave the audience to explore the equivalent approaches.